Last time tulikuwa tunaongea kuhusu single phase motors, AC motors, and I had given you assignment mwende msome na mwandike notes kuhusu single phase synchronous motors and single phase series motors. That was the assignment last week. You go write notes and diagrams and see how these two single phase motors operate. Na mimi sasa nikaongelea kuhusu single phase induction motors. Now we talked about how single phase induction motors are not self-starting. How when you supply AC current to a single phase induction motor, the stator field, the stator windings usually produce a pulsating flux. Now this pulsating flux tuliona last week that it can be resolved as being two fluxes that are rotating in the opposite direction. There is one flux that will be rotating in the forward direction, then there is another flux that will be rotating in the backward direction. Now last time kile mali tuliacha ni tulikuwa tunaongea kuhusu the effect of this pulsating flux ambayo inakuwa produced by the stator fields, its effect on the rotor circuit. Now we had drawn some circuits, tukasema that the flux that will be rotating in the forward direction and the flux that will be rotating in the backward direction, kwa sababu ya mambo ya slip, will have the equivalent circuit of the rotor in the forward direction and the equivalent circuit of the rotor circuit in the backward direction. They will be different. Now we talked about slip, tukasema that slip is the difference. Slip is the difference between the synchronous speed. Difference between the synchronous speed, the speeds of the field produced by the stator windings and the rotor speed, which is usually n. And if you're told to calculate speed, you'll find the synchronous speed. The slip. If you are to calculate slip, you'll take the synchronous speed minus the rotor speed all over the synchronous speed. Now, tukasema that at standby, the rotor, we explained the operation of a single phase induction motor at standstill. Tukasema if the rotor is not moving, the rotor imesimama, the pulsating MMF produced by the stator windings by supplying a single phase current is established. And I had drawn this. Nilikuwa nimechora hii. I had drawn this diagram, a very simple diagram indicating the distributed windings in a stator with the one phase supply, and we have a rotor. Now when you supply single phase current into the stator windings, a pulsating flux is produced, and this pulsating flux will act along the axis of the stator windings. Now this pulsating flux induces another flux. It will induce a flux in the rotor. The pulsating flux will induce a flux in the rotor, and this flux, the rotor flux, will be acting in the opposite direction. It will oppose this flux, the flux causing it. It will act in the opposite direction, but it will act along the same axis. Now these fluxes oppose each other, and can be this law. We can find out how these fluxes oppose each other by stating that Lenz's law. Lenz's law says that the current produced by flux will be in the direction opposing it. Now that is when the rotor is stationary. Now when the rotor is running, we said that we can make a rotor. Remember that a rotor of a single phase induction motor is not self-starting. And we say that we can make the rotor self-start. I mean, we can make the motor self-starting by, no, we can make the rotor move by using our hands. We can tunaweza twist na mkono ikasonga, or we can add auxiliary circuits into that rotor, which causes the rotor to produce its own flux, and this flux is that the flux produced by the stator and the flux produced by the rotor interact, producing deflecting torque. We had talked about this. I don't want to go back kwa sababu tutakaa sana hapa. Now today I wanted to introduce nimechora hii circuit. I was just trying to go back so that I can introduce this circuit. This is a circuit, the equivalent circuit of the rotor, and we have the effect of the rotor. Well, the flux, the stator flux, as it moves to the forward direction and as it moves in the backward direction. The flux, like we got mesema that the stator flux can be resolved as having two fluxes rotating in the opposite direction. Now, these fluxes induces a current in the rotor, such that a single phase motor can be seen as having two rotors, two rotors, each having half reactance and half resistance. Now, when I draw this equivalent circuit of the rotor at standstill, I have drawn the equivalent circuit with the voltage. We have V1 as the supply voltage from the AC source and the current. This R1 is the resistance of the stator, and X1 is the reactance of the stator. Xm over 2. Now this here is the circuit of the rotor when it is influenced by the forward moving flux. And this here is the circuit of the rotor when influenced by the backward moving flux. Now, if the rotor is at standstill, the value of resistance will be over 2. The value of the reactance will be over 2. The value of resistance here will be R2 over 2. And the value of reactance will be X2 over 2. At standstill, the rotor will be seen as having half resistance and half reactance. But now when the rotor starts moving, we have to take into consideration slip. And we said the slip is the difference between the synchronous speed and the rotor speed. Now, the synchronous speed, slip in the forward, the speed of the flux, the resistance of the rotor circuit when it is moving in the forward direction is taken as R2 over 2S, S being the slip, and the resistance of a rotor moving in the backward direction is taken as R2 2 minus S, where S is a slip. In our last class we had seen how we get slip in the forward and the backward direction. Now, when we use this slip, this circuit, so that we can come up with the parameters. We can be able to find the current, we can be able to find the voltage of this motor. Now, there is something I want to introduce known as impedance. I want to introduce something known as impedance. Now, this is the total resistance of a circuit when you take into consideration resistance, capacitance, and reactance. When you have a circuit ambao umechorea, you have an inductor, you have a resistor. Sometimes when you have a capacitor, when you're told to find the total resistance in that circuit, we don't call it resistance, we call it impedance. And impedance is the collective resistance, collective ohmic resistance due to the resistor and reactances, capacitive reactance and inductive reactance. Now, this impedance is usually denoted by Z. Now I want to see how this comes into play. Kwa sababu now in this equivalent circuit of our motor, we have the resistor. We have a resistor, we have an inductor. Now, in a motor, in that motor, you will not find a resistor and an inductor connected to it. But we resolve it as having a resistance and reactance, inductive reactance, because this motor is a coil. It consists of wires, windings. Those windings have resistances. The material has internal resistance, and the inductance comes about because this wire, these conductors are wound into coils. So essentially it is seen as a circuit of a resistor and an inductor connected in series. Now, when we are calculating the impedance of this circuit, confirm the total impedance in this circuit, total, will be equal to the impedance, because in the stator, will be equal to the impedance in the stator, R1 plus this, plus the impedance due to the forward field, the forward moving field, plus the impedance due to the backward moving field. Now, impedance in the stator will be given by the resistance, stator resistance, plus the inductive reactance. We have to put this because it is a complex number, and we will see how to calculate this in our calculators. Make sure you have a calculator A-type that has this. Make sure you have a calculator ambayo iko na AG and absolute, so that you're able to calculate these complex numbers. Now this is the impedance in the stator. Now the impedance, because of the forward moving field, I will label it ZF, is equals to R2. Now this is in series, so we'll add the resistances because it is connected in series. Now in our in our rotor circuits, because of the forward moving flux, you'll find that this resistor and this inductor are connected in series, but our magnetizing inductors is parallel. It's connected in parallel with these two. So therefore, the impedance, because of the forward moving field, will be up. Can you hear me by the way? Unajua naweza kuwa naongea na labda mnisikii. Are we together? I might be talking to myself. Now, the impedance, because of the forward moving field, will be, we find the resistances, the resistances in this circuit. So we'll find we'll first compute the resistances in series, and then we compute the resistances in parallel. Now, the resistance in series will be R2 prime over 2s plus j x2 over 2. Remember, when finding when you have two resistances, when you have resistances that are connected in series and you want to find the total resistances in that circuit, and you only have two of them, we find it by the total resistance in a circuit. Itakuwa the product over the sum of those resistances, R1 plus R2. If you have two resistors in a parallel configuration, and they are connected to a power source. Now in this case, our resistor in series is easy. This one will be computed as one resistor, and this will be another resistor. Now we want to find the resistance in series. Now we'll take the resistance in series and we compute it as one. We multiply by the resistance in parallel, the magnetizing reactance, inductive reactance, over the sum. It's product over sum. Now the sum is this, R2 over 2s plus j x2 over 2 plus j xm over 2. When we are dealing with the reactances, the inductive reactance, we always add the j to indicate that it is a complex value. Now this is the inductance in the rotor circuit. No, this is the impedance in the rotor circuit due to the forward moving flux. Now we do the same. The inductance, no, the impedance, because due to the backward moving field in the rotor, ZB will be given by R2 over 2 minus S plus X2 over 2 times J XM over 2 all over R2 2 minus S plus J X2 prime over 2 plus JXM over 2. What we are doing in this case is that we are saying that resistors in parallel, when you only have two resistances in parallel, we find the total resistance by taking the product of those resistances plus over the sum of the resistances. When you have two resistances in parallel configuration, the total resistance in that circuit will be given by R1 times R2 over R1 plus R2. This value over here can be taken as our R1 and this value as our R2. Now, are we together up to that point? Are we together? Now, once you have found the impedance, the total impedance, which we have said is Z1 plus ZF plus ZB, then it is very possible to find the current in that circuit. And how will we find the current in that circuit? It will be using Ohm's law, V is equals to IR. The current will be the voltage supplied in that circuit. This indicates the phase angle of the voltage, supply voltage, which is 0. It is always at 0 degrees, divided by the impedance. The impedance that you have gotten at whatever angle that you will get. We will do the calculation and see at which angle that you will get. This is now resistance, the total resistance in that circuit. Now let us try this example so that we can see. We have been told that a two-pole to 40 volt 50 hertz single phase induction motor has the following constants referred to the stator. Now the value of the stator resistance is 2.2 ohms. The value of the stator inductance, inductive reactance, is 3 ohms. The value of the rotor resistance is 3.8 ohms, and the inductive reactance in the rotor is 2.1 ohms, and the magnetic reactance is 8.6 ohms. No, 86 ohms. And you have been told to find the stator current. And find the input power when the motor is operating at this is part A of the question and part B of the question. When the motor is operating at load, full load of 2820 RPM. Full load, now this speed will be our rotor speed, the speed at which the shaft is rotating. You've been told that a two-pole 240 volt 50 hertz one single phase induction motor has the following constants referred to the stator. We have the stator resistance and the stator reactance as 2.2 ohms and 3 ohms. We have the rotor resistance and the reactance, the inductive reactance, as 3.8 ohms and 2.1 ohms. And we have the magnetizing reactance as 86 ohms. Number one, find the stator current. And number 2, you find the input power, given that the speed at which the rotor is rotating is 2820 RPM. Tumeandika hiyo swali? Tumeandika. Okay. Let me know when you have written the question so that we can continue. Now, we have been told to find the stator current and the input power. Now, the first thing that we'll have to do is we'll first have to find the slip. Remember that this induction motor, single phase induction motor, is moving. So we won't have, remember I said that the equivalent circuit of an inductive motor when it is stationary, when the rotor is not moving, is we won't have that condition of slip. This will be R2 over 2, R2 over 2. But when it starts moving, then we have to take into consideration slip. And the slip due to the forward moving flux is S, and the slip due to the backward moving flux is 2 minus S. I think we had written that in a previous class. Now, how do we find slip? Slip is given as, we say that it is the synchronous speed, the speed of the magnetic, the revolving magnetic field due to the stator winding, minus the rotor speed, the speed at which the motor is moving, the rotor is moving, divided by the synchronous speed. We have been told that our road speed, our speed is 20 to 2820 RPM. How do we find the synchronous speed, NS? It is given by 120 times the frequency divided by the number of poles of that motor. And you have been told that our frequency, our supply frequency is 50 Hertz, and the number of poles in that motor is 2. It's a 2-pole machine. So our synchronous speed, therefore, will be given by 120 times the frequency being 50 Hertz divided by 2. What will be our synchronous speed? (3,000 RPM). Now we can therefore find this, the slip. Slip is NS, which is 3000, minus the load speed, which is 2820 divided by 3000. What will be the value of our slip? Fiona, what will utakona kama Fiona akona sisi?
I was taking my calculator.
Usiachwe nyuma tafadhali. Now the value of slip will therefore be 0.06. Mtafuta bairo nyingine. to use a red biro, so nitatumia red biro, so I hope you don't mind. So the value of our sleep will therefore be 0.06. Now the current, the stator current I1 will be given by the supply voltage V divided by the total impedance in that circuit. Now we say that the total impedance in that circuit will be given by the impedance in the stator plus the impedance due to the forward moving flux plus the impedance due to the backward moving flux. Now the impedance due to the stator Z1 will be equal to R1 plus JX1. R1 plus JX1. The value of R1 to Shapatio, which is 2.2 ohms, plus J, always include that J to indicate that this is a complex number. J and X1 is 3 ohms. Now, ZF, the flux due to the forward moving field in the rotor. The impedance due to the forward moving field is therefore, tulikuwa tumeandika the formula, ama tulikuwa tumeandika, we had written ZF is equals to, nataka mniambie, that formula that we had just written sahi, when you replace the values ambazo tumepatia, tutakuwa tunaandika nini? Remember that ZF, the impedance due to the forward revolving field, is given by the resistance plus the rotor reactance times the magnetizing reactance divided by the sum. Now we are trying to find the total resistance. Now let's replace the values, because we already have the value of the rotor resistance, we already have the value of the rotor reactance, and we already have the value of the magnetizing reactance. We have been given in the question. We have R2, X2 and Xn. Now ZF is therefore equal to our value of R2. R2 is 3.8 over 2. We have S. We have just found the value of the sleep, which is 0.06. 3.8 times 2 multiplied by 0.06 plus J, the value of the rotor reactance is 2.1 ohms. 2.1 ohms. So plus J 2.1 divided by 2 times J, the magnetizing reactance was 86 over 2 over the same now 3.8 6 plus J 2.1 over 2 plus we are finding the total resistance in that circuit, that rotor circuit due to the forward field. Are you together? Mpaka hapo tuko sawa? Are we together?
Yes, yeah, together.
You know you have to lazima museme kitu ili nijue bado mko. Now let's open this. We want to simplify this. The 3.8 divided by 0.06 times 2 unapata ni 31 point.
1.66. 667.
667 plus 2.1 divided by 2 ni ngapi? 1.05 j multiplied by j 86 divided by 2 ni 43 all over the same 31.67 plus j 1.05 plus j 43. Now let's open this bracket. J 43 times 31.67 utapata ngapi? 43 times 31.67 is 1361
6.81.
j. Now j being a complex number, when you multiply j times j unapata -1. J times j is a -1, so this value will therefore be minus 43 times 1.05 minus 45.15 over 31.67 plus 1.05 plus 43 j. It is 44.05 j. Now what I want you to notice here, when you have this complex number multiplied by this complex number, j times j is negative. Unakupatia negative value and the j disappear. Now what you are left with is this. This is the impedance in the rotor circuit due to the forward moving flux. ZF is negative 45.15 plus j 1361.81 over 31.67 plus j 44.05. Now how do we calculate this? We want to change it to polar form. We want to find the value of the resistance in ohms, and then we want to find the phase angle. You want to find the resistance in ohms, the real value, and the imaginary. You want to find the real value, and then you want to find the imaginary value. This is the real value, this is the imaginary value. Now we want to change this real and imaginary to polar form so that we can get now the value of the resistance in ohms and the value of the impedance, in ohms, and the value of the phase angle. Now how do we do that? Take your calculator ambayo uko nayo. Make sure you go to mode, press mode, and go to complex 2. Now we can be able to calculate our complex numbers. Now for us to be able to find the value of resistance, the value of resistance, we will take, we want to, so for us to be able to change this complex number to polar form, we will press shift. You press shift, finya shift, and then finya tuanze na absolute. I want you to be able to get this in your calculator. So Paul and Fiona, umeweza kufanya hiyo? Tafuta mahali hapa. If you have the same calculator as I have, iko mahali hapo chini. Tafuteni mahali tu pameandikwa absolute and argument. Fiona, unaona mahali pameandika absolute na argument? Ama Fiona ni kama alienda. Fiona alienda. Paul, have you been able to find it?
does not have the arguments.
Uone kabisa.
Hakuna. Si unaiona mwalimu kazi yangu yenyewe.
Acha nione. Hebu nionyeshe na nini? Oh. Let's see. Hakuna argument kabisa.
Hakuna.
Absolute iko.
Absolutely hakuna.
Hakuna mahali popote pameandikwa absolute ama
Inaangalia hakuna difference.
so itabidi ukifanya mahali hiyo question itabidi utafute calculator kama hii ambayo natumia. Now I will just continue so that when you find the calculator kama hii, you can be able to do those calculations. Now, once you get the value of ZF, once you get the value of ZF in complex form, you change it to polar form. So what you do is you take your calculator, unafinya shift and mahali ambapo absolute iko, you get absolute. Once you get absolute, you input the values, kwa mfano the numerator, minus 45.15 plus J 1361.81. So minus 45.15 plus, now in our calculator, hatuna J, we don't have J, but we have I. We'll use I in our calculator because we don't have J. This is the absolute I'm talking about in an argument. So plus 1361.81 finya I 1361.81 I. Now what that gives you is the polar, the value of the value of this complex number, the value of the complex number in polar form. Now we want to find the angle of that this complex number, angle yake. So we'll do the same as we have done with the absolute, but now we'll press shift and argument. We use argument to find the angle, the polar angle. So we input the same values, 31.67. No, it is minus 45.15 plus 1361.81. Since we don't have J in our calculator, we use I to give you the angle. Angle 91.8.9. Let's put 0.9. 91.9 degrees. Now we do the same with the denominator. Shift absolute. Value of the denominator is 31.67 plus 44.05 I. You get that the 54.253, and the angle will be shift absolute, no, shift argument. We input the values again, 31.67 plus 44.05 I. Yet that the angle is 54.29 degrees. Now we can be able to in this, when it was in its complex form, we could not have divided these values, the numerator and the denominator, but when it is in its polar form, we have now values, real values. So it is now possible to take 36 1362.56 divided by 54.253. So 1362.56 divided by 54.253. To get there, we get 25.15115, and the angle 115. Now this is the resistance, the value of the resistance, some of the impedance, the real one, 25.115 ohms. And now the angle. Now how do we find the angle? We don't divide the angle, we subtract. So 91.9 minus 54.229. 91.9 minus 54.29. That will give you the value of the angle. Degrees. We have 25.115 ohms at an angle of 37.61. So these first two values you divide to get the resistance, some of the impedance. The angle you subtract. Are we together? Sawa. Now, since remember that this is ZF. Now remember that our Z1 was in complex form. Z1 was 2.2 plus J3, and now we have found that we have our ZF in polar form. So we want to convert this back to complex form so that we can be able to find ZT, the total impedance, Z1 plus ZF plus ZB. As it is right now, we cannot take Z1 in its complex form and add it to ZF. So we have to change this back to its complex form. And how do we do that? We take this value, this 25.115 cos of this angle, that 7.61. This will give us the real part of our complex number. 25.115 sine of this angle, that's 7.61. This will give us the complex, some of the imaginary part, the J part. So 25.115 cos of 37.61. This gives me 19.896 plus, now for the imaginary part, 25.115 sine of sine of the angle, which is 37.61. This gives me the imaginary part. So our ZF will therefore be 19.896 plus J, this value, 15.327. Now we have our ZF. If you were to add this ZF plus the Z1, it is possible because we will take the real part plus the real part, 2.2 plus 19.896, and then we can take this imaginary part and we add it to this imaginary part. It is possible. Mpaka hapo tuko sawa? Are we together up to that point?
Yeah.
Now we do the same for the backward field, ZB. We do the same for ZB. Now how do we find ZB? We had written the formula. ZB is equals to, niambieni haraka haraka. How do we find ZB? Tunapataje ZB? Now ZB is given by the resistance, the rotor resistance, divided by 2. Remember that the resistance of the forward moving flux and the resistance by the back moving flux is the same, is equal when the rotor is at standstill. But when the rotor is moving, then we have to take into consideration the slip. Now the slip due to the backward moving flux is 2 minus S, and the slip due to the forward moving flux is just S. Now this plus J x2 over 2 times the magnetizing in reactance over 2 minus S plus JX2 over 2 plus JX and over 2. Nikiandika hivi sijui kama mnaelewa. When you are finding the resistance of two resistors connected in parallel, it is product of a sum. R1, R2 over R1 plus R2. Sijui nikiandika, when I write it like this, I don't know if you understand what I'm writing. Unaelewa?
Yeah, naelewa.
Okay. Fiona, unaelewa? Are you sure? Fiona. Umenyamaza sana hii class, so I need to know if you're on the same page.
Naanza na parallel first, then ndio series.
Sasa ukiangalia our diagram, we have these two are connected in series, and this one is in parallel to these two. Now, this circuit ni kama resistances in series. We have, in parallel. When you have two resistors in parallel, we have R1 and R2. When you're finding the total resistance in this circuit, it is the same as saying the total resistance will be R1 R2 over R1 plus R2. Okay? Now, when you have two resistors in parallel, the total resistance of those resistors is the product of those resistances over the sum of those resistances. Now, when you look at a diagram, I don't know if my diagram is clear. When you look at our diagram, these two are in series. These two are in series, but these two are in parallel with this one, the magnetizing reactance. So when you look at our formula, kwa mfano hii ya backward, when you look at our backward, the impedance, the total resistance due to the backward field, it is inaichukulia kama R1, and this I'm taking as R2. Because these are in series, we can add them together. So tunaweza ichukulia as one value, R1, and this is in parallel, so we can take it as R2. Now we said that the total resistance for resistors in parallel is the product R1, R2 over R1 plus R2, which is the same in this case. We're taking the product of those values over the sum of over the sum. Sijui kama mnaona hiyo comparison.
Yeah.
Okay. So hapo tuko sawa. Okay. Now, Fiona, tuko pamoja? Uko na swali? Okay. Now we have found the impedance due to the forward, the total resistance due to the forward field. Now the resistance due to the backward field will be given by this formula. Now we already have this value, so all we have to do is replace them. We already have the value of the rotor resistance, which is 3.8 over 2 minus 0.06. That is the value of our slip. Plus J, the rotor reactance is X2, 2.1 over 2 times J, the magnetizing reactance is 86 over 2, divided by the same R2, which is 3.8 over 2 minus 0.06 plus J 2.1 divided by 2 plus the magnetizing reactance, which is 86/2. Now, when you simplify this, we get that this 3.8 2 minus 0.06 times 2, so 3.8 divided by that is that. So J 43, this 86 divided by 2, J 43 into brackets, this value is 0.9794 plus J 1.05 over J 43, no, yes, J 43 is 86 divided by 2 plus J 1.05 here upper 2.1 divided by 2, and then this 3.8 divided by 2 times 2 minus that, this is plus 0.9794. So the backward flux when simplified, so J times this will give you, so 43 times that answer, so it will be 42, J 42.113. So this now 43J times 1.05J will be minus 45.15. The J and the J, when you multiply them, will become negative. So 43J plus 1.05J is 44.05J plus 0.979. Now that is the value of backward impedance, some of the total resistance of the rotor circuit due to the backward flux, but now in real. It's a complex number. We have a real in an imaginary part. Now we have to convert that as well into its polar form, so that we can be able to find the actual value and the value, so that we can be able to divide these two. So now the impedance, we start with the numerator. And how do we convert this complex number to polar number? We will take the calculator again, and we press mode, and we go to the complex. We change the calculator to complex mode. Now, how do we find the value? We take shift, then mahali kuna absolute, where we have absolute, finya absolute. We input the numerator. Our numerator is minus 45.15 plus J, no, 42.113. And I said since we don't have a J in our calculator, what we have is an I. We'll use that I. That gives you the value of the real value of that impedance. So ZB is equals to 61.742. We are changing it to polar form, so that is the real part. Now the value, now we find the angle. And how do we find the angle? So shift, argument, shift, mahali kuna arg, finya. We input the values of the numerator. Minus 45.15 plus 42.113 I. That will give you the value of the angle, 137.99. Now that is our numerator. What about our denominator? We do the same. Shift, absolute. You input the values of the denominator. So 0.979 plus 44.05 I, to give you the value 44.06. At what angle? Shift, argument, 44 point, you input the values denominator 10. 0.979 plus 44.05 I to give you the value of the angle 7.3. Now we can be able to calculate now the impedance because it is it's not in complex form anymore. Now for this part we divide, and for this part the angles we subtract. So 61.742 divided by 44.06 gives you 1.4013, and the angle, this is our impedance, and our angle is 137.99 minus 88.73 to give you an angle of 49.26. Now this means that our impedance is 1.4, our impedance due to the backward flux is 1.4013 ohms at an angle 49.26 degrees. Okay, now we have to convert it back into complex form so that we are able to add the previous values, ZF and Z1. Now how do we convert it back to complex form? To get the real part, we take 1.4013 cos of this angle 49.26, and to get the imaginary part, it's 1.4013 sine of the angle 49.26. This gives you so the impedance due to the backward flux is, for the real part, 0.91 24. Okay, 45 plus
0.91 45.
Okay, 0.9145 plus J plus J
J is 1.0 plus J
1.0
is 1.0662.
Sawa. Now let us list what we have. We have Z1, we have ZF, and we have ZB. Z1 we had found it as 2.2 plus J3. ZF tumepata kama 119.896 plus J 15.327, and our ZB tulipata as tumeipata sahi kama 0.9145 plus J 1.062. Now Z total will be Z1 plus ZF plus ZB. So we'll take these real numbers, we add them, and we'll take the imaginary and add them as well. Yeah? So 2.2 plus 19.896 plus 0.9145 napatia ngapi? 23.011 plus J, so 3 plus 15.327 plus 1.062, so J 19.389. Now this is the value of the total impedance, but it is in complex form. It is in complex form, so we change it back to polar form. So how do we change it back to polar form? Narudi kwa calculator. Make sure that your calculator is in complex. So unafinya mode 2, you press 2. Shift, press shift and then absolute to change it to polar form. So 23.011 plus 19.389 I. So since we don't have J, to give you 30.091 ohms at an angle of, how do you find the angle? Shift, press shift, and then argument. The same value. We put the same value, 23.011 plus 19.389 I, to give you the value of the angle. So the total impedance, the total resistance in our circuit is 30.091 ohms, occurring at an angle of 40.117. Mpaka hapo tuko sawa? Are we together up to that point? How did we start? If we recap kidogo, tulianzaje? We found our sleep. Let us go back kidogo. Ndio tuone kama tuko sawa. Tulianza by finding the sleep. And how did we find the sleep? We took the synchronous speed minus the load speed divided by the synchronous speed. We had been given the load speed as 2820. We found the synchronous speed by taking 120F over P. We had been given the frequency, we had been given the pole, the poles. We are able to find sleep. Now the question was asking us to find the stator current and to find the input power. Now how do we find the stator current? We take the voltage, supply voltage, divided by the total impedance. And how do we find the total impedance? ZT, Z total, is Z1 plus ZF plus ZB. We have the value of Z1. We have calculated the value of ZF upper, and we have calculated the value of ZB. Now Z total will therefore be Z1 plus ZF plus ZB. How did you find the values of Z1? I mean ZF na ZB. Kuna ile formula nimewapatia. You just replace the values. The only part that you will calculate, or you'll use a calculator, is now changing that value from the complex to the polar form, so that you're able to finally get that the total. Now, so that you're able to find the total impedance, the total resistance in ohms. We have to change, kwa sababu when you're calculating the values of reactance in this rotor circuit, lazima tuweke J, and once we introduce J into our calculations, then that number changes to become a complex number. So we have to change that number to and fro, from polar to complex, from complex to polar. The only thing I wanted to show you today is how to change that. Na sijui kama mmeelewa. Have you understood how to change a number from the complex to the polar form?
Yes.
Sawa. Now we now have the value of total impedance as 30.09 ohms at an angle of 40.17 degrees. Now, stator current will therefore be given by the voltage, supply voltage, divided by the total impedance, the total resistance. Now, our supply voltage was 240 volts from the question, and this supply voltage is being supplied at an angle of 0 degrees, and our resistance, total resistance, the total impedance, is 30.091 ohms at an angle of 40.117 degrees. Are you together? The phase angle is 40.117 degrees. So our current will now be 240 divided by 30.091, 7.9796 98 amperes at an angle of, we take this minus, so 0 minus negative 40.117, 40.2, no, 40.1. Now what does this mean? This means that our current, the current in this circuit, this current upper, the current flowing in the stator current is lagging the supply voltage. Now, what do I mean when I say it is lagging the supply voltage? Now, remember that this is an alternating current. You'll find that, let's say our voltage is inaanzia hapo. Let's say this is our voltage. Now, our current will therefore be, itakuwa nyuma, itakuwa inakuja after. Our current will be coming after the voltage in that alternating sequence. Labda, if we complete this, itakuwa namna hiyo. You see that this, our voltage inaanzia, let's say at 0, but our current itakuwa inaanzia an angle 40.117 after. It will be starting an angle 40.117 after the voltage has already started. So when you're asked to find now we have been able to find the current at 7.97, but it is lagging the voltage 40.117 degrees. Are we together?
Yeah.
Now the second question was asking us to find the input power. The power is given as VI cos theta, ama the cos of that angle. We know that power is equals to VI, or it is equals to I squared R, or it is equals to, what is another formula of finding power? Power is equals to VI, power is equals to I squared R, power is equals to, I can't remember the other, but the one that we're interested in, P is equals to VI cos this, because the current is lagging the voltage at a certain angle, so we have to include that angle. Therefore, the power will be given by the supply voltage, which is 240. This is now the input power. 240 times the current, which is 7.976 multiplied by the cos of 40. 40.117. What will be the supply power? Ama the input power into that motor? 240. Yes?
Why are you not using the negative?
No. Oh, this negative doesn't mean that the angle is negative. No, it just means that this angle is the current is lagging. When it is positive.
When the angle is negative, we use the alternate angle.
No, we use the absolute value of that angle. We don't include this negative. Okay? Sikumaanisha that our angle is negative. It just means that the current iko nyuma. If I was to draw it as a phasor diagram, this is our voltage because it is at 0 degrees, but now our current itakuwa nyuma at 40.117. This doesn't mean that that our current is, this angle is negative. It just means that iko nyuma. It is starting at a later inaanza after. So we won't use the negative. We'll just use this. But once you are writing, utasema that this is, the current is 7.976 amperes lagging at an angle of 40.117 degrees. Sir Paul. So our power will therefore be 240 times 7.976 times cos of that, which gives us 240 times 7.976 times cos of 40.117. You'll get that the supply power, ama the input power into the motor is 1463.88 watts. That is the power that is required to power, ama to move our motor. 1463.88 watts. Now that is now I would say that is a very simple calculation of induction motor, single phase induction motor. When you're told to now, we are now finding the performance. We are calculating to get the performance of that motor. Mpaka hapo tuko sawa? Fiona?
Not really.
You know, it's because you missed the other class, kwa hivyo inaleta shida kidogo. But what I want, lakini kile nilikuwa nataka tu kuonyesha ni that when you have a single phase motor, utapata kwamba the stator flux, the flux ama the rotating field produced by the single phase supply to the stator windings pulsates, and once it pulsates, it induces. Once it pulsates, we have a single phase supply into the rotor, and we have the stator distributed stator winding. So once you connect this stator winding to the single phase supply, it produces a flux which is pulsating. Now this pulsating flux, tuliona last time that it can be resolved as two fluxes rotating in. This pulsating flux can be resolved as two rotating fields, but they are rotating at the same speed but in opposite direction. One will be rotating in the forward and the other will be rotating in the backward direction. Now the effect of these fluxes, these two revolving fluxes, ni kwamba that our motor can be seen as having two rotors, and this rotor will be the fluxes. The forward flux will influence the rotor in a particular way. Will be influence the rotor differently from the backward flux, and we see this when we include slip. Once the rotor starts moving, when the rotor is stationary, then we can see that the effect of the pulsating flux is that we'll have two rotors having these values, the values of the resistance and the values of the reactance as half. The effect of the forward and the backward itakuwa nusu-nusu. So the resistance will be over 2, the reactance will be over 2, and the magnetizing reactance will be over 2. But now once the rotor starts moving, then that we have to take into consideration the aspect of slip. The impedance due to the forward moving flux, the slip itakuwa S. The slip due to the backward moving flux will be 2 minus S. Are we together? Now the impedance due to the forward moving flux, tumepata hiyo formula ndefu niliwapatia, and the impedance due in the rotor due to the backward moving flux nimewapatia. The only difference utaona katika hizo formulas mbili ni that in the forward moving flux we have to take into consideration S. Our slip is different in the forward moving field than in the backward moving field. The slip in the forward moving field is S, and the slip in the backward moving field is 2 minus S. So we can go through that that example again and see whether you'll understand. If you don't understand, then we will do it again. But now that is us calculating seeing the performance of a single phase induction motor. Is there a question? Question? Paul, do you have a question? I'm swali. Yes?
Yes.
Nakupata. Nakusikia. Yes.
Input power when it is operating, so like when we are given the output power.
Now, output.
Input power tunaweza kupata
tutapata, and we'll see that sana sana when we come to now the 3-phase induction motor. Single phase induction motor hesabu yake hatufai kuwa tunaiguzia sana kwa sababu unaona ninaleta shida kwa yes,
hesabu ya efficiency of the motor
tutaingia when you come to the calculation sasa the 3-phase. Hii calculation ya single phase nilikuwa hata tu kupitia juu hata sijaguzia mambo ya power kwa sababu I'm not really sure whether I'm supposed to be doing that, teaching you how to find the power ya single phase, but I just wanted you to do it so that in case iletwe kwa mtihani you won't be hautashindwa kufanya. But once we start doing now 3-phase induction motor, when we'll see that we'll see the calculations. We'll do air gap power, we'll do mechanical power, we'll see how the losses will affect the output power so that we can see the difference between the output power and the input power. Now, acha nimalizie hii single phase. Now, single phase, the single phase types of single phase motors inategemea how we start them, and they can be capacitor start, we can be capacitor run, it can be split phase or shaded pole. Now, the one that we've been talking about is split phase. The one we talked about last time, the split phase. You add an auxiliary winding, and now the single phase induction motor becomes a two-phase induction motor. So you find that the main winding, the stator winding, will have a flux, and that flux will induce another flux in the auxiliary winding. That flux in the auxiliary winding is equal 90 degrees out of phase. So being out of phase means that those two fluxes will interact to produce a starting torque on the rotor. Hiyo ndio tuliongea about last time. Now capacitor start and will have a capacitor. I don't know if you can be able to see. Now this is the let me enlarge this photo. Now this is the split phase. We have the main winding, the stator winding, and then we add an auxiliary winding hapo kando. We have the rotor. So the effect is that the auxiliary winding is put 90 degrees out of phase to the main winding, the stator winding. So when you power, when the alternating current, the single phase supply ikiingia kwa the stator winding, that pulsating flux is produced. Once produced, then the auxiliary winding, the effect of the auxiliary winding is that the flux now produced by the auxiliary winding, being out of phase, 90 degrees out of phase, then it will interact with the flux of the stator winding, and this will produce a deflecting torque in the rotor. So the rotor will now be able to move. Now this is the split phase. Now capacitor start is that we have a capacitor connected in series with the auxiliary winding. Now what this does is that it increases. If you look at our phase angle, the current in the main the current in the main winding and the current in the auxiliary winding, unaona hii angle. This is the resultant current. This is the supply voltage. As you can see, the supply voltage is always at a phase angle 0. Now, when you look at now this circuit ambayo imekuwa connected to the capacitor, is that the effect of the capacitor is to increase this phase angle. We use the capacitor to increase the phase angle. Now, the disadvantage of this is that it's high cost. Itakuwa expensive. With a high phase angle, then the motor itakuwa na high starting torque. So use it for high starting torque applications. Now capacitor run. Now capacitor start, we have a centrifugal switch. What happens is once the effect of the capacitor is felt, once the motor starts running and it reaches 75% of the synchronous speed, the rotor that is, then you can turn off the synchronous. I mean, you can turn off the auxiliary winding on unazima hii. And how do you do that? You introduce a centrifugal switch into that circuit. Now this is for the split phase and for the capacitor start induction motors, single phase induction motors. But now for the capacitor run induction motors, this capacitor connected in series with the auxiliary winding is in actual. It is not cut off from these two. The auxiliary winding and the capacitor are not cut off from the circuit, so they run throughout. And what this does is it increases as well it simplifies the construction of that circuit. It also decreases the cost because now you have removed the centrifugal switch. And then we have capacitor run, capacitor start, capacitor run, single phase induction motor. We have the capacitor used for starting connected to a centrifugal switch. So we cut off this one once the rotor reaches around 75% of the synchronous speed. And this capacitor, the capacitor used for the running operation is left to run. So it is not disconnected from the circuit. Now the shaded pole, we have the shaded pole. Now I won't go into detail about these types of induction motors. I just wanted to mention them briefly so that you can know that these types of we have different types of single phase induction motors. We have capacitor start, we have capacitor run. The one that we've been mentioning sana sana is a split phase, and we also have shaded pole single phase induction motors. Now, how do we control the speed of these motors? Now, the common, the simplest is having an external resistor. We have external resistance connected to the motor. Now, what this does is it controls the supply voltage into the motor. When you vary the resistance, this is a variable resistance. When you have a rheostat connected to the motor, when you increase the resistance, the external resistance, then the voltage in the voltage supply increases. When you reduce the resistance, that is, if you have a steady supply of current, the current doesn't change. When you reduce the voltage, the resistance, then the supply voltage into the motor reduces. So that is the most common, the simplest way of reducing of controlling the speed into the motor by changing the supply voltage into the motor. Now, this has disadvantages. Hello.
Yes.
Sijui nimepotea kidogo, sijui kama mmeshika, tumeachana wapi? Okay. I was saying that how we control voltage how we control the speed in a single phase induction motor is we connect an external resistance to the motor. The simplest way is we connect an external resistance to the motor. Now what this does is it controls the supply voltage into the motor. So when you increase the resistance, the external resistance, then using the principle of the Ohm's principle, then the supply voltage will also increase. We can be able to increase the supply voltage if we have a constant supply of current, and if you reduce the resistance, then the supply voltage reduces. Are we together? Now, this has disadvantages. The biggest disadvantage is there is power loss. The power loss, because of the resistor, there is power lost into the motor. The winding losses. The internal resistance in the wires. increases the power loss. Now the size of the physical size is also a limiting factor, because if you have a large motor, then you have to have a large external resistance. You have to have your resistance will be big. The durability and the maintenance of this external resistance will also come into question, kwa sababu it is an additional component, so you have to keep on maintaining it, you have to keep on servicing it, so then you'll have to keep on utakuwa una change, you will have to replace it over and over again, kwa sababu it is a mechanical part. Now the other way we can control the speed of a single phase induction motor is solid state control. This I'm not really sure about. I'm not so conversant with it, but what I know is that you can be able to control the voltage, since it's a AC. Also AC voltage in a change, there will be a positive and a negative value. Then it is possible to control the voltage in the positive and also control the voltage in the negative using solid state control, voltage control. But I'm not so sure about how it works. You can go find out more in detail. I will also go find out in detail how the solid state works. But I know that it can be able to control the voltage when it is in the positive side of the positive side, and you can also be able to control the voltage when it is in the negative side. Now I think nimepitia single phase. I don't know whether I should introduce three phase now. Should I introduce three phase induction motors? Now what I'll do is I will play a small video so that we can have an idea of how three-phase induction motors work. So please tell me whether you can be able to hear and whether you can be able to see.
Have a discussion about working of three-phase induction motor. For understanding the principle of three-phase induction motor, we first look at the basic constructional feature of this type of motor. This motor mainly consists of two major parts. First one is stator. Stator of this motor is made up of number of laminations of cold grain oriented silicon steel to reduce hysteresis and eddy current loss. The inner periphery of this cylindrical stator is provided with number of slots. A three-phase winding is so similarly distributed among these slots that when a three-phase power is supplied, a rotating magnetic field is produced. This magnetic field rotates at a synchronous speed. Second one is rotor. Rotor of a three-phase induction motor consists of cylindrical laminated core with parallel slots. Conductors are heavy copper or aluminum bars, and they are short-circuited by an end rings, which fit in each slots. Now, initially when the rotor is standstill, the flux of rotating magnetic field cut every solid conductor of the rotor. As the rotor conductors are stationary and sinusoidal stator field is rotating, there will be a change in flux linkage with the rotor conductor. As a result, there will be an induced current in the rotor conductors as per Faraday's law of electromagnetic induction. Whenever this current starts flowing through the conductor, it reacts with the magnetic field. Again, as we know that current carrying conductor inside a magnetic field experiences a mechanical force. Hence, here a mechanical force will be experienced by the rotor conductors. Due to this force, the rotor will start rotating inside the stator, and the rotor will try to achieve the speed of rotating magnetic field. Once the rotor achieves the speed of rotating magnetic field, there will be no relative speed between the rotor and the rotating magnetic field. Hence, there will be no current induced in the rotor conductor. That means at that condition, no mechanical force acts on the rotor conductor. Hence, the rotor decelerates. As the rotor decelerates, again a relative speed between rotor and rotating magnetic field is re-established, and hence there will be again current induced in the rotor conductor, which causes mechanical force to act again on them. As a result, the rotor again accelerates to reach the speed of the rotating magnetic field. Due to this phenomenon, the rotor will never reach the speed of rotating magnetic field, and also the rotor will not stop rotating till the three-phase power is there in the stator. Actually, the rotor rotates with a speed slightly less than the speed of rotating magnetic field. This is how a three-phase induction motor works. Thank you.
Sijui kama tunaweza kusikia vizuri. Have you been able to hear?
Yeah, we've had.
Now, the difference between
Yes.
now the single phase and the three phase is the supply current. Moja itakuwa inakuja single phase and another is coming itakuwa three phase. Now, we've seen that the stator is made of laminations of high grade steel. Sijui kama mliona hiyo video ikianza. We have sheets of metal ambazo zimewekwa in layers. That's what we mean by laminating. Unaweka in layers, and then within those layers kuna slots in the inside of the, I don't know if I have I do not have a diagram, but the laminations, those sheets of steel are put in layers, and then once they're put in layers, then there are slots within those layers. So we have winding, three-phase windings within those layers, the stator windings. Now the stator of a three-phase and a single-phase are usually the same. The construction is the same. The only difference ni moja iko na three-phase windings na nyingine iko na single-phase windings. Now the rotor of a three-phase ni tofauti kidogo. We'll have something known as a squirrel cage or a wound rotor. Squirrel cage in the sense that the rotor has copper bars or aluminium bars ambazo zimewekwa, they are skewed, meaning that they are parallel to each other but they are at an angle. They are not straight, they are put at an angle. And then these ends of those copper bars are shorted by something known as an end ring. Hii hapa. This kitu ambayo imeunganisha these copper bars is known as an end ring. We have short-circuited, we have connected those copper bars together. So this is known as a squirrel cage, kwa sababu inafanana na squirrel cage. Now, what happens is that these copper bars are skewed, they are put at an angle so that they prevent magnetic clocking between the rotor and the stator. They are used to quieten, to reduce vibration in the rotor when it's rotating. Now, as you've heard that when a current conductor, when put in a magnetic field, when it interacts with a magnetic field, then it experiences a mechanical force. This is Lorentz law. When you have a conductor, a current conductor in a magnetic field, then that conductor will experience a force. Now, since we have so many conductors in this squirrel cage rotor, then the cumulative force will cause this rotor to rotate in the direction of the rotating magnetic field, which is produced by the stator. Remember that we have a three-phase supply to the stator now. and each phase, each winding will produce its own flux, its own rotating, its own flux, and these fluxes, the flux in, let's say, let me say that I have a flux A. I mean, I have a coil A, B, and C. So the flux is produced by coil A, coil B, and phase A, phase B, and phase C will interact to produce a rotating magnetic field in the air gap. The air gap is the space between the rotor and the stator. Now, the rotating magnetic field due to the stator rotates at synchronous speed. Now, this magnetic field will interact with the rotor. The carrying the rotor, this kwa mfano now the squirrel cage, and this rotor, these conductors will experience a force, a mechanical force. Now this force will enable, will make the rotor now start rotating in the direction of the rotating magnetic field, due to the stator, which is rotating at synchronous speed. Now, I think we've had the part ambapo wamesema that once itafika mahali that the rotor speed and the synchronous speed are the same. Now, once this time ikifika at that point, then the rotor will reduce speed, ama ita decelerate. Reason being, since this motor is working on the principle of electromagnetic induction, then there has to be relative speed between the rotor and the magnetic field, the magnetic field due to the stator. If there is no relative speed, then there will be no current being produced being induced in the rotor, and then there won't be any voltage. I mean, there won't be force there won't be any mechanical force to turn the rotor. So once that rotor decelerates, then that relative speed is again, it's attained again. So utapata that the rotor itakuwa inafika the synchronous speed, then it decelerates kwa sababu there is no mechanical force being produced. Then once it decelerates, then that relative speed is attained again. Now you see that the sleep, we'll still have to talk about sleep in this perspective again, kwa sababu sleep is the difference between the speed of the rotating magnetic field in the stator, in the air gap, and the rotating the rotor speed. This is the sleep. Now, the frequency of the rotor current, the current induced in the rotor circuit, the principle of electromagnetic induction again. When you have a stator flux, I think I talked about it in the single phase supply. When you have a three-phase supply to the stator windings, then a magnetic flux, a magnetic field will be induced. Now, this magnetic field, once you have a conductor interacting with that magnetic field, then it will induce voltage in that EMF in that conductor. Now, this EMF produces a current, generates a current. So now this current ambayo tumekuwa tukisema flowing through the rotor, once this carrying conductor interacts with the magnetic field rotating in the air gap, then it experiences a mechanical force which enables it to rotate. The reason why this three-phase induction motor is self-starting. It's self-starting. Reason being the phases. Remember that three-phase, they are 120 degrees electrical out of phase with each other. And so this, if this is our phase A, then this is our phase B, then this will be our phase C. They are out of phase with each other. So there will be a magnetic flux due to this phase, a magnetic flux due to this phase, and a magnetic flux due to this phase. And the collective what now? The collective magnetic rotation of those fluxes will now enable this rotating this rotor to rotate. Now, let us look at something kidogo. Mpaka hapo tuko pamoja Bwana Paul?
Yeah.
Umeelewa tofauti ya 3 phase na single phase?
Yeah, in terms of construction.
In terms of construction. Now, now remember that nimesema that a 3 phase Now, I've said that a 3 phase induction motor, stator, the basic parts of a motor. We have the stator and we have the rotor. Sawa. Now the stator is the stationary part, and the construction of the rotor, of a single phase and a three phase stator, usually the same. The only difference is that one is connected to a 3 phase distributed winding and the other is a single phase distributed winding. Now the rotor can be of 2 types. We have squirrel cage and we have slip ring or wound rotor. Now the one that I was explaining is upper squirrel cage. Now what the squirrel cage has copper bars. The windings are in form of copper bars. Now these copper bars are usually shorted. What do I mean by shorted? Zimekuwa connected to each other by something known as an end ring. Known as an end ring. Then we have the shaft, which provides mechanical power output, connected to an end ring. Now, once that 3-phase supply is supplied to the stator windings, then the effect of the alternating current in each winding produces an alternating the current in each winding. Some the phase phase A, then we have maybe another phase and another phase. Each of that current is alternating. Let's say this is phase B and this is C. The supply current is a 3-phase supply, so this current produces a sinusoidal MMF, a sinusoidal MMF. What happens is this the effect of these currents, since they are alternating, they produce a pulsating MMF whose amplitude and direction will be dependent on the instantaneous current. But now let's achana here. Now the pulsating MMF due to the current in the phase, let's say phase A and phase B, will be that it will produce a rotating magnetic field, a rotating field in the air gap. And I've said that the air gap is the space. Let's say this is our stator. This is our stator of that of a 3-phase induction motor, and this is our rotor. And this is the air gap, the space between the stator and the rotor. So we'll have a rotating magnetic field, a revolving magnetic field in the stator. In the air gap due to the 3-phase supply. Now, when we talk about the squirrel cage, now this we have seen that these motors, the induction motors, operate on the principle of electromagnetic induction. Now, the pulsating the magnetic field produced by the alternating current, the 3-phase alternating current, will produce a stator. Will produce a rotating revolving magnetic field in the air gap. This revolving magnetic field will interact with the winding in the rotor. And in this case, I've said the winding in the rotor are copper or aluminium bars. Now this revolving magnetic field will interact with our copper aluminium bars, and it will induce EMF in those it will induce EMF in those bars, in those conductors. Now, since these conductors are shorted, they form a closed circuit. They are shorted together by something known as an end ring. What happens? We have current being produced in these conductors. Let's say this. Let me draw this again. Let's say these are our conductors. We have the end ring over there. Yeah? Since these conductors are shorted, then we have current produced by the induced EMF. Now, this current, due to this current, remember that we have said due to a law known as Lorentz law. This law states that a force, a current carrying conductor, which is in a magnetic field, a rotating magnetic field, will experience a force. Confirm this conductor upper will experience a force in that direction. This conductor will experience a force. This conductor will experience a force. This conductor will experience a force, and so on and so forth. So what happens is that these collective forces will make our rotor rotate, and it will follow the direction of the rotating magnetic field in the air gap. Are we together? Now that is the principle of operation of a squirrel cage. Na nikasema that once that rotor starts rotating, then itafika mahali that rotor speed will be equal to the speed of the rotating field in the air gap. Now once this happens, then our force, the force being experienced from the rotor, becomes zero. Why? This is because the current, the rotor current, the current in the conductors has become zero as well, because there is no relative motion between the rotor and the rotating magnetic field, because they are all rotating at the same speed. Therefore, there has to be one has to be behind the other, so that we have current being produced in the conductor, and because there is a current in the conductor, then this conductor then experiences a driving force, a rotating force. Without relative motion, then there won't be force. So once there is no force, then this rotor in a reduced speed, it decelerates. Once it decelerates, then there is now that relative motion is attained again. So utapata that once that relative motion is attained again, then the stator field is able to induce voltage in the conductors, the rotor windings, and now the induced voltage then produces current, and that current enables the conductors to experience a force, which enables the rotor to rotate by the principle of Lorentz law. That is the working of a squirrel cage. Squirrel cage, three-phase induction motor. That is a very simple explanation of a squirrel cage induction motor. Now, what I want you to do is you go find out how a slip ring or a wound rotor works. The differences between a slip ring and a wound rotor. Both have three-phase supply. Three-phase, but there is a difference. The construction of a three-phase slip ring and the construction of a three-phase squirrel cage is different, but the principle of operation is similar, but ziko tofauti. Now find out, andika in your notes mahali how a slip ring rotor works. Are we together?
Yeah.
Now for today nitachia hapo, so that on Monday we will see how the rotating field is how the rotating field is produced, and we'll do some calculations on the three-phase supply. I've given an assignment katika Google Classroom. You go find out how we start, the different starting mechanisms of a three-phase induction motor. We have direct online. We can connect the three-phase induction motor directly to the supply. We can start using a transformer. So find out how to start the three-phase induction motors. But for today tutaachia hapo. Go try that example tena ya single phase, so that when you come to the three-phase calculation, tutaona the differences.